Alright, hello everyone. Today we're going to discuss energy emission spectrum, um, different kinds of it. So, emission spectra, absorption spectra, continuous spectrum, line spectrum, and we'll take hydrogen as an example and how to find it. So, what is an emission spectrum? Emission spectra are produced when photons are emitted from atoms as excited electrons return to a lower energy level. So basically, photons is an energy given out after electrons get excited. They move up to a higher energy level. They stay there for a fraction of a second, and then they return to a lower energy level. So, and energy emitted is called photon, and this is what gives a specific energy wavelengths. So the different versions of spectra and you need to be able to distinct a continuous spectrum from a line spectrum. So an example of a continuous spectrum would be when a white hot metal object, such as an incandescent light bulb filament, it emits the full range of wavelengths, producing a continuous spectrum, including all the colors of the rainbow from red to violet, as you can see on the highest diagram. So the continuous spectrum means that there are absolutely no gaps in it. And while a line spectrum is the opposite, it's a spectrum where there are gaps in it. Emission spectrum and absorption spectrum are examples of line spectra. If a pure gaseous element such as hydrogen, for example, is subjected to an electrical discharge, the gas will glow and it emits radiation. And this refers to the diagram in the middle. And so if this light from the gas goes through a prism, it will give out emission spectrum. So as you can see, there are just a few lines over there. And each element will have their own lines. So they can't be the same for every single element. It's like a barcode if you think about it. Now talking about the last diagram. So if a cloud of a cold gas is placed between a hot metal and a detector, an absorption spectrum is observed. So this consists of a pattern of dark lines against a colored background, and the gaseous atoms absorb certain wavelengths of light from the continuous spectrum. So yes, like again, the light passes through the prism, so the prism is very important to find out the different spectra. And absorption and emission spectra are widely used in astronomy to analyze light from stars, so this is one of the examples of how spectra are used in the real world. To make it easier for you to memorize it, you can just associate the spectra with Pink Floyd logo. As you can see, there's like a perfect example of it. However, here you can only see the visible light. And electromagnetic radiation, it consists of full range of different wavelengths, and visible spectrum is only a tiny fraction of those wavelengths. So one of them are gamma rays. Gamma rays have the most amount of energy, but the shorter wavelengths. So the energy of electromagnetic radiation is inversely proportional to the wavelengths. Therefore, radio waves, which have the longest wavelengths, they have the least amount of energy. So, if you think about real-world applications, gamma rays are the most harmful ones for you, while radio waves don't affect you, they hardly affect you at all. And so, as you can see, visible spectrum is really one of the tiniest fractions of the electromagnetic spectrum. And each color has its own wavelengths. So, for example, violet has a wavelength starting from 380 and goes up to 450 nanometers, while red has the longest wavelengths of all the colors, of all the visible colors. Don't forget the visible part because it's really important. So red has it from 620 to 750. And so if you think about it, violet is closer to ultraviolet, and ultraviolet has one of the most has more energy than infrared radiation. And on the next diagram, you can see this is the eye sensitivity function, and usually we kind of absorb more as a green light, and we have trouble seeing violet and red. And then examples of how this can be used in science are flame test colors. So, for example, when you burn lithium, it gives out red flame. But when you burn copper, it gives out blue-greenish flame. And when you heat potassium, it gives out lilac flame. The colors are due to the excitation of electrons in the metals by the heat of the flame. As the electrons lose the energy they have just gained, they emit photons of light. And, well, these photons of light are like what you observe. And so, let's move to our example of hydrogen spectrum. So, how we find it? First, it goes as gas discharge tube containing hydrogen. It gives out certain kind of glow or light. As this glow goes through the slits and onto the prism. In the prism, this light divides up into multiple colors. As you can see, there are violet, blue-violet, green-blue, and red. And all of those colors correspond to their specific wavelengths. And as we can see on the next diagram, hydrogen absorption spectrum and hydrogen emission spectrum, they, if placed together, they will form a continuous spectrum. However, while they're separate, they're line spectra. On the hydrogen emission spectrum, we can see hydrogen alpha line, which is the red one, and its wavelength is 656 nanometers. And this means that it falls onto the Balmer series. And Balmer series is when electron gets excited and it falls back onto the energy level 2. And when electrons go back to energy level 2, this means that they go to Balmer series. So, and when they get excited and go to energy level 1, they are included in the Lyman series, and when they fall to energy level 3, they're in the Paschen series. And on the next diagram, we can see that Balmer series, it is located in the visible and ultraviolet regions of electromagnetic spectrum, while Lyman series is located only in the ultraviolet region, and Paschen is located only in the infrared region of electromagnetic spectrum. So don't forget that this is determined by the final energy level of electrons. So it doesn't matter to which energy levels they rise up to, it matters to which they fall down to. And there are a few equations that will help you out with finding the wavelengths, the frequency, and we can go through a few examples. So, the question, the wavelength of green light is 522 nanometers. What is the frequency of this radiation? And the equation that we're going to use is C equals to frequency of the radiation, which is letter V, times the wavelengths, which is this new Greek symbol. So the speed of light is 3.0 times 10 to the power of 8 meters per second. And if we're going to use this number in our equation, and we are going to use this number, we need to convert the 522 nanometers into meters first. So this will be 5.22 times 10 to the power of negative 7. And so basically what we do, we divide the speed of light by the wavelengths. And we get 5.747, this is rounded up, times 10 to the power of 14 hertz, because frequency is measured in hertz and wavelengths is measured in meter, and the unit for energy is the joule. Alright, so this moves us to the next equation, which will probably help you too. Is ionization energy, which is E, equals to the speed of light times Planck's constant over lambda, which is the wavelengths in meters. So this will help you out further in finding the first ionization energy, successive ionization energy, and my classmate will discuss this more in depth. You will find the link on his video in the description for this one. So a little bit of recap. So please just remember that the energy of electromagnetic radiation is inversely proportional to the wavelengths. So the shorter the wavelengths, more energy it has. And you need to remember the order of the rays. So starting from the shortest wavelengths and going to the longest wavelengths, it goes as: first there are gamma rays, then there are X-rays, then there's ultraviolet, then there's visible light, then there's infrared and radio waves. So gamma rays are usually 0.0001 nanometers, while radio waves can reach up to 100 meters. And another topic that we need to discuss is the electron configuration and how electrons are placed in the atom and around the atom. So first there is an s orbital. So the first two electrons go into the s orbital, and it is just like a circular sphere. Then the next level is called p level. Well, the first one is called S level. So the P level, there are 3 axes in the P level: Y, X, and Z. And each axis can hold up to 2 electrons. And so in total, the second energy level can hold up to 6 electrons. So this is when we tie up, and I hope that you enjoyed this video. I hope that you find it educational and hopefully you learned something from it. If you still have questions, I'm gonna post some links in the description to some educational websites that will hopefully help you out. And thank you guys for the attention. Thank you so much. Good luck and have a happy life and enjoy chemistry.